Okay, it looks like it's all set.
All right, great. In that case, welcome everyone. Today we have John Brundan from University of Oregon, who is going to give us two talks on the Heisenberg category. So yeah, thank you, John.
Okay, well, thank you for inviting me. I actually never spoke about this stuff, even though it's a couple of years old, so it'll be an experience. What I want to try and do is talk about this Heisenberg category, which was introduced by Michael in, well, about 10 years ago, a little more than 10 years ago, and kind of prove the first theorem about it, which is that it's Grothendieck ring. The Grothendieck ring of the Heisenberg category is the Heisenberg algebra. So I've got to define all of these terms, and I'm actually going to try and explain the proof. So I always find that's kind of a challenge to explain a proof in 50 minutes, but I'm going to give it a shot. And as a result, I'm kind of going to just keep to the purest, simplest first example of the Heisenberg category, since it was first introduced. There's a whole load of generalizations and quantum analogs and so on. But just to try and get to this proof, I'm going to keep it as narrow and focused as possible so that I can go through that. So let me see, I'm going to work always just over the complex numbers today. So everything will be C-linear. I'll probably even forget to mention that everything's C-linear. That's only really important in those places where I start using the group algebra of the symmetric group Sn. Of course, I need to be in characteristic 0 when I use semi-simplicity of that group algebra. So we've got this Heisenberg monoidal category is going to show up. That's capital H highs. And the theorem I'm trying to explain the proof of is that the Grothendieck ring of the Heisenberg category is the Heisenberg algebra. So that's little h highs. I can't do fancy fonts when I'm writing by hand, so I have to use capital H and little h for categories and algebras. So this was essentially proved by Khovanov in 2010, and there was really just one kind of important step that was missing back then, and we filled in that step with Alistair Savage and Ben Webster to finish this proof. I'm going to, as I said, I'm going to try and talk about this most special narrow case. That theorem that I've written up here, it's what I call central charge k equals -1. In fact, this Heisenberg category has a parameter k, which can be any integer attached to it that's central charge. And I hope to have just a little bit of time at the end. Oh, I need a black pen. There we go. To add the more general central charge k to the story. Actually, that's quite a significant extension of the theorem. It's somehow much harder to get to general central charge, and it needs a completely different technique as well, which we called categorical co-multiplication. But I might not get there, so that's the way it goes. But the original story is, for me, central charge k equals -1, and that's what I'm going to start off by going through. So here we go. So because I'm going to try and explain a proof, I actually need some theoretical tools. So I've got to do a little bit of teaching to remind you of these sort of tools. So I need to talk a little bit about Grothendieck groups to start with. Let's try and keep it simple. If I just have a unital algebra, then of course everybody knows that K0 of A, the Grothendieck group of that algebra, that means the split Grothendieck group of finitely generated projective. I'm going to work with left modules. Okay, so that's just the free abelian group generated by isomorphism classes of finitely generated projectives, modulo this relation that P is P prime plus P double prime whenever you've got a direct sum decomposition. P is P prime direct sum P double prime. But let me see, I'm not, the world I like best is the world of finite dimensional algebras. So let's just think what happens if A is a finite dimensional algebra rather than an arbitrary unital algebra. So then you can also consider this thing I call just K0 prime of A, which is the usual Grothendieck group of the Abelian category. of all left A modules. So this is the free abelian group on isomorphism classes of all finite dimensional modules. And there the relations come from short exact sequences in that abelian category. Okay, so there's K0, which is a good thing to consider for any unital algebra. And then K0 prime, which I try to only consider when I've got some sort of finiteness assumptions like finite dimensional algebras, is my favorite world, of course. So let's stick with the case when A is a finite dimensional algebra just for a second. In that case, the Grothendieck group K0 prime is very easy to understand. It's just got a basis. It's a free Z module with basis given by the classes L1 through Ln, where those guys are just a full set of irreducible left A modules. Okay, so in this finite dimensional world, this is not a very rich invariant, this Grothendieck group. It's easy enough to understand. And still in that finite dimensional case, if you let Pi be the projective cover of Li, then the isomorphism classes of the Pi's give a basis for the split Grothendieck group, K0 of A. Okay, so this is kind of basic stuff. In fact, these two Grothendieck groups in this finite dimensional setting, they're really just dual to each other. So these bases, the Pi's and the Li's, they're dual bases with respect to the Cartan pairing between K0 and K0 prime. So if P is a projective and L is a finite dimensional module, the Cartan pairing PL, that's just the dimension of the Hom space from P to L. Okay. The problem is we're not going to be in the finite dimensional world, but I always find it helpful to think about that nicest possible situation to understand what's going on. So let's just keep finite dimensional just a little bit longer. So A is still a finite dimensional algebra. Now let's fix some idempotent E in A. And I've got my list of the irreducible left A modules, L1 through Lm plus, why did I write M plus N? I'm not sure, I meant Ln there. Let's fix that. Oh, tool's not working very well today. Right, so those are my complete set of irreducibles. And let's just group them so that the first M of them, the idempotent E is 0, and then on the rest of them, the idempotent E is non-zero, okay? So the ones on which E is 0, those irreducible A modules, they're just the inflations of irreducible modules from that quotient algebra. So AEA is a two-sided ideal, and that's just the quotient by that two-sided ideal. And if E acts as 0 on the irreducibles, those irreducibles factor through to that quotient. So that first bunch of them, L1 through Lm, they're just inflations from that quotient algebra. Whereas that second bunch, the ones on which E is non-zero, well, for those L's, you can hit them by the idempotent E. That's the idempotent truncation of L. And then that's a module over the algebra EAE. Okay, so this is sort of totally well-known basic fact that for these ones, the ELs give you a full set of irreducible modules for that idempotent truncation, EAE in there. And so if you just think about this, just consider these bases given by the classes of irreducibles for this K0 prime, it follows immediately that there's this short exact sequence of Z modules here. So this is the K0 prime of A, where the classes of all the L's are a basis. This is the K0 prime for this quotient algebra, and this is this K0 prime for the idempotent truncation. And this first map in this short exact sequence is just induced by the inflation functor, and the second map is this idempotent truncation functor. So it's just kind of immediate from thinking about these bases, the way I've grouped them, that there's this short exact sequence of Z modules here. It's very easy, very trivial thing. So that's K0 prime. And then if you take duals using this Cartan pairing, you deduce immediately from that there's this short exact sequence between the split Grothendieck groups. So I reversed all the arrows here. So the split Grothendieck group of EAE maps to the split Grothendieck group of A, maps to the split Grothendieck group of the quotient algebra. And the maps are induced by these functors tensoring with these bimodules. Okay, so that's a sort of a trivial fact which we use all the time when working with finite dimensional algebras. But the important point for us, when we're not going to have finite dimensional algebras today, is that that last short exact sequence I wrote down actually works in general. So I do not need the assumption that A is a finite dimensional algebra. So I'm going to call this the basic lemma, this observation that this fact, which for me is a triviality in the finite dimensional world, it's actually true for any unital algebra. So here it is. For any unital algebra, there's this short exact sequence between split Grothendieck groups. It's just the same one as I had before, except to get it in this generality, I need one assumption. I need to assume, so here's the algebra A, here's the quotient algebra A over EAE, where E was this idempotent that was fixed. This is the quotient map. I need to assume that there's an algebra splitting of that quotient map. So there's a homomorphism sigma back again, so that the composition is the identity. Okay, so I need that splitting assumption because, well, the naive proof that I gave you in the finite dimensional case by dualizing doesn't work. But if you have this splitting going in the other way, you can define a functor going back this way, because this homomorphism sigma lets you make A into a module over the quotient algebra. And then tensoring with that bimodule lets you come up with a map in the other direction, which turns out to split the maps that we've got. And using that, you can, in a fairly elementary way, just prove again that you have this split short exact sequence between split Grothendieck groups. So we're going to need that. That's our kind of going to be our basic tool, and that's the it's a sort. It should be a very well known fact, and totally well known for finite dimensional algebras. I never actually found it in the literature. It should be in the 1960s literature on algebraic K-theory, but I still couldn't find it written explicitly anywhere. But it's a general result. The other tool I need from K-theory is what I'm going to call Quillens Lemma. So this we learned actually already from Michael's original paper where he noticed that this was relevant. I'm just stating a special case. Quillen proved a much more general theorem in his 1973 lecture notes dealing with higher algebraic K-theory, but we just need the following. So this is just a specialization. So I need A here, my unital algebra. I need it to be positively filtered.
John, sorry to interrupt you. There's a couple of questions in the chat.
Yep. If you don't have the algebra splitting, do you still get the short exact sequence for K0? I don't know the answer. I suspect not, but I can't give you a counterexample. The algebra splitting is essential for the way for the proof. I'm not a good enough expert about algebraic K-theory to know what happens without that. I suspect there's probably a long exact sequence in K-theory, but I'm not really sure. And Aaron, is this not just the functoriality of K0? I think it's more than that, but so I'm not sure I can answer that question. So there's another short exact sequence which is easy, where you have the K-theory of the ideal AEA in there, and that comes immediately from the functoriality of K0. But here I don't have at the beginning. I don't have the K-theory of the ideal AEA. I've got the K-theory of this new algebra EAE. So to me that's the thing that's slightly different in there. Okay, so okay, so there's the long exact sequence. So again, when I looked this up in the 1960s K-theory literature, this, instead of the K-theory of EAE appearing there, you always see the ideal AEA appearing in this long exact sequence. So anyway, it's a basic lemma, and we since we couldn't really find a satisfactory reference, we just gave a naive proof of it. I think it's an important fact. Okay, so back to Quillens Lemma. So I want a positively filtered algebra. So you should think of something like a universal enveloping algebra of a finite dimensional Lie algebra. So that this is positively filtered, and the PBW theorem tells you that the associated graded algebra is the symmetric algebra on the same vector space G. And so you need a couple of hypotheses. You need that the bottom piece in that filtration, A0, so that's actually a subalgebra of A. You need that that's semi-simple. And then if you think about A0, it's of course a module over the associated graded algebra A. And the second hypothesis is that A0 has to have finite projective dimension as a module over the associated graded algebra. And then Quillens Lemma says that the inclusion of A0 into the algebra A induces an isomorphism between split Grothendieck groups. So if you apply that in the case of universal enveloping algebra, the associated grade is just the symmetric algebra, and so it's easy to check those two hypotheses. A0 is just the ground field in that case. So you get that the split Grothendieck group of a universal enveloping algebra is just, I wrote C, why did I do that? No idea. It's just the same as K0 of a field, so the Grothendieck group of vector spaces, which is just Z. Another example, again, I wrote C, that was, again, I'm too used to writing C. You can apply this, actually, if you apply what I just did to an Abelian Lie algebra, then that universal enveloping algebra is just a polynomial algebra in n variables. And so as another special case, you get that the split Grothendieck group of a polynomial algebra is Z. Of course, we know vastly more here because of the Quillens-Lemma theorem, but that just sort of fits that in there. Relevant for us later on, taking split Grothendieck group commutes with direct limits. And so actually you can take this n here and you can just let n go to infinity and deduce from this that actually the Grothendieck group of an infinite rank polynomial algebra is a copy of Z as well. So you can pass to infinite rank there. The third example, which is going to be important for us, it's somehow a little bit like the polynomial algebra case, except I'm going to add in a symmetric group Sn as well. In fact, what I'm going to look at is this degenerate affine Hecke algebra, DAHN. So it plays an important role in this Heisenberg story. So this is a tensor product of the polynomial algebra and the group algebra of the symmetric group. Those two algebras are both subalgebras. And then there's these interesting relations telling you how a simple transposition commutes with a polynomial generator. It's not quite the smash product because of this +1 term that appears in the commutation relation. In fact, the degenerate affine Hecke algebra is filtered, and the associated graded algebra is exactly that smash product. So because it's filtered, we're in a situation where we can apply Quillens Lemma, and you have to check the hypotheses from Quillens Lemma, but that's fairly straightforward. And so as a result, you deduce that the Grothendieck group of degenerate affine Hecke algebra is, and again, I'm writing nonsense there, it's the same as the Grothendieck group of the group algebra of the symmetric group. Let me just write in a conjecture there. Actually, I think that all projective modules over these degenerate affine Hecke algebras should just be induced from projective modules over the group algebra of the symmetric group. I think that's quite an interesting problem. I tried a little bit and couldn't do anything. course, that would be somehow a generalization of Quillens to this setting. Okay, so we're going to be considering C-linear categories rather than unital algebras, but it's just the same story. If capital C is a C-linear category, what I often like to do is just think about the path algebra of that category, and that gives you an algebra A. So that's just the direct sum over all objects x and y in the category of the morphism space in the category from x to y, and you can define a multiplication on that coming from composition in the category. That's not a unital algebra, but it's what I call a locally unital algebra. Some people call it an idempotented algebra. So it's an algebra with a collection of mutually orthogonal idempotents, 1x. Those are just the identity endomorphisms of the objects of C. And with that dictionary, then you can easily upgrade everything you know about unital algebras to locally unital algebras, and so to C-linear categories. For example, the Grothendieck group of the category C is just the same as the split Grothendieck group of that path algebra A. So just isomorphism classes of finitely generated projectives as before. I guess if you have an idempotent of some object of the original category, you can look at that left ideal AE, that's a finitely generated projective left A module, and then you can take its class, and that gives you something in the Grothendieck group, right? So idempotents give you elements here. And the only other thing to mutter here is that if the category C, that C-linear category, is actually monoidal, that's what's going to be interesting for us, then actually this Grothendieck group isn't merely a group, it's actually a ring. And the way these left ideals generated by idempotents multiply in that ring is just coming from the tensor product on that monoidal category. So E tensor E is the tensor functor on that monoidal category. Okay, so that's the background on K-theory that we need. Now let's start talking about Heisenberg. So I need to tell you what the Heisenberg algebra, that was my little h Heis, is. So we should start off by thinking about the ring of symmetric functions. So that's little s sim. Okay, and I'm going to assume that everybody is comfortable about the ring of symmetric functions. I've got elementary symmetric functions, complete symmetric functions, power sums, and then of course there's a basis for that as a free Z module given by the Schur functions labeled by partitions. Okay, so that's symmetric functions. And if you have a symmetric function f, I'm going to use the notation f plus for the endomorphism of that Z module sim that's given by left multiplication by f. And then I'm going to use the notation f minus for the adjoint endomorphism. There's this usual inner product on symmetric functions where the Schur functions are an orthonormal basis. And so f minus just means the adjoint endomorphism with respect to that inner product. And then the Heisenberg algebra, little h Heis, that's the subring of the ring of endomorphisms of that Z module generated by all of those f plus or minuses. So the f pluses are the kind of positive ones that are multiplication, and the f minuses are these adjoints. So that's the Heisenberg algebra. An easy way to understand it is to think about the power sums, and if you calculate the commutator of Pm plus with Pn minus, so that's multiplication by the power sum, and Pn minus is the adjoint operator. It's fairly easy to see that that commutator is just minus the inner product Pn, which is 0 if m doesn't equal n, and it's n if they're equal. And when you see that commutation relation, you recognize that as coming from the infinite dimensional Heisenberg Lie algebra. That's this H. So the infinite dimensional Heisenberg Lie algebra, it's got generators Pn plus or minus, and then a central element C, and the Lie algebra relation for that is that the commutator Pm plus and Pn minus is that inner product times the central element C. And all the other pairs of generators of the Heisenberg Lie algebra just commute. And so you see this Heisenberg ring that I've got up here, there's a minus there. That's the specialization where I want to replace the C, the canonical central element, by -1. So actually what we're looking at in this algebra Heis, it's the universal enveloping algebra of the Heisenberg Lie algebra specialized at central charge C equals -1. In fact, it's a Z form for that specialization. And as a Z form, it's got this beautiful basis coming from the Schur functions, these products S lambda plus S mu minus partitions lambda and mu give a basis for this Z form as a free Z module. I think that's everything we need to know about the Heisenberg algebra. So that little h Heis. Okay, and it acts on sim, the ring of symmetric functions. So now we get to the Heisenberg category. The point is, what we're trying to do is we're trying to categorify the action of the Heisenberg algebra on symmetric functions. So we all know how to categorify the ring of symmetric functions. Little sim is categorified by big sim. So for me, I use this. I don't think people use this terminology, but the category sim, the symmetric category, that is the free symmetric monoidal category on one object. So let me expand what that means just a little bit. So there's one generating, so big sim, it's a monoidal category. It's a strict C-linear monoidal category. I just need one generating object, which I just denote by a single line, 1. And you need just one generating morphism, which is just that crossing. So I'm using the string calculus. I'm sure everybody in this seminar knows the string calculus, so I'm not going to go over that. So you just need the crossing, which goes from 1 tensor 1 to 1 tensor 1. And the only relations you need, because you want to be symmetric monoidal, are that the crossing squared is the identity, and then you need the Reidemeister 3, well, the braid relation, whatever you like to call that relation, and that's it. So maybe there you recognize the Coxeter presentation for symmetric groups, but it's really much more natural just to present the whole monoidal category in one go, and then it's extremely simple. But in this monoidal category sim, the morphism space between objects n and n prime, well, it's 0 unless n equals n prime. And when n equals n prime, that morphism space is just the group algebra of the symmetric group. So the symmetric category is just a kind of a neat way of packaging all the group algebras of all symmetric groups together. So then I think the most classical fact there is in representation theory is that the Grothendieck ring of this monoidal category of the symmetric category is the algebra of symmetric functions. Okay, and I mean, I guess that's probably Frobenius theorem. And the isomorphism takes the isomorphism class of the spect module, capital S lambda, labeled by partition lambda, to the Schur function, little s lambda. Okay, so I mean, often you usually don't say this using the language of monoidal categories. You normally just think in terms of representations of symmetric groups. And so then the tensor product that I've got becomes this thing that people usually call induction product. So if you have an SM module X and an SN module Y, the induction product, well, you just take their outer tensor product as a module over SM cross SN, and then you embed that as a maximal parabolic subgroup of SM plus N and induce. No, I'm seeing there's a question come in. Do you need to say Karoubi completion, or does it come for free somehow? I buried that in my definitions. By K0 of sim, if you like, I mean the Grothendieck ring of the additive Karoubi envelope. But when I defined K0 earlier, I'm talking in terms of finitely generated projective modules, and so I don't need to say that. Okay, so this is totally the most classical fact in representation theory, that the Grothendieck ring of the symmetric category is the ring of symmetric functions. So now we want to find what acts on this symmetric category sim, and that's going to be this Heisenberg category, capital H Heis. So to find out what that is, we should think about what acts on the symmetric category, right? So capital N sim. So if you have any category, you can look at the strict monoidal category of endofunctors and natural transformations. That's what we're looking at here. We're looking at that strict monoidal category for the symmetric category. What functors act on sim? What are the natural transformations around between those functors? So the most obvious functor that I think I can come up with, I'm going to call it capital S lambda plus. So that's just taking the tensor product with the spec module S lambda. Right? So that's just this induction product with spec modules. And that functor has that, so that's kind of an induction functor. It has an adjoint, which I'm going to call S lambda minus. So I've got these two obvious endofunctors, S lambda plus and S lambda minus, of the symmetric category sim. Actually, of projected modules over the symmetric category sim, I should say. Actually, up to passing to summand, you don't need all the S lambda pluses and S lambda minuses. You just need the what I call HM plus, which is induction with the trivial module, and what I call EN minus, which is the adjoint for the sign representation there. Actually, even better, you don't need HM plus and EN minus. You only need the first one. You only need H1 plus and E1 minus, which I'll just call induction. So that's just the usual induction functor from Sn to Sn plus 1, but for every n. And in my diagrams, I'm going to denote that by an up arrow. So up arrow is that simplest induction functor. And you just need E1 minus, which is that simplest restriction functor, which I'm going to denote with a down arrow. So you need those, providing you've also got the crossing endomorphism here, this natural transformation from doing induction twice to itself. So that's going to be denoted by this crossing. I should quickly say what that is. So by transitivity of induction, that's just tensoring with the bimodule CSN plus 2 over CSN. And that bimodule has an endomorphism given by right multiplication by the last transposition. So that's a natural transformation from induction squared to induction squared. That's going to be this thing I'm just going to denote by the crossing. And once you've got that, then you can define these Young's idempotents and project big compositions of induction down onto these S lambda plus functors in there. Okay, so that's really all you need. And to get the same story for the adjoints, well, you need this rightward cup and rightward cap, which are just the unit and the co-unit of the canonical adjunction between induction and restriction. So you need to throw those in. And there's one more kind of well-known endomorphism, one well-known natural transformation from induction to induction, which I'm going to denote by a dot. So that's given in terms of the bimodule that you're tensoring with, the group algebra of Sn plus 1, that's given by multiplication by Xn plus 1, which is the sum of all transpositions that end n plus 1. That's the Eusis-Murphy element. So those are sort of the obvious candidates for endofunctors and natural transformations that we've got acting on sim. And then to discover this Heisenberg category, you just think about what are the relations between these natural transformations. And really the most important one is the Mackey isomorphism. So this is the isomorphism between induction, restriction, direct sum the identity functor, and restriction induction. And if you look up the proof of that in this special case, you see that the isomorphism is given explicitly by a certain column vector of natural transformations. And I'm going to denote those by this rightward crossing and rightward cup. And the rightward crossing is just the upward crossing that I had composed with the co-unit, but with the unit and co-unit of our induction. So it's sort of rotating this crossing through 90 degrees. And that gives you a natural transformation from induction restriction to restriction induction, which is that first morphism we need there. And then the adjunction gives us this natural transformation from the identity functor there. And that column vector is exactly the Mackey isomorphism in this special case. So that's kind of discovering the Heisenberg category, which I imagine was the thinking Michael went through a decade ago. So the Heisenberg category highs, finally, is the strict C-linear monoidal category with just two generating objects up and down. They correspond to induction and restriction. And then you need four generating morphisms. This upward crossing, the rightward cap and cup, and this dot, which came from the Eustace-Murphy elements. And the relations are sort of clear, right? We need those relations that are just kind of a copy of the symmetric category. This relation with how a dot passes the crossing, that's the relation these Eustace-Murphy elements satisfy, which come from these degenerate affine Hecker algebras that I had at the beginning. That was that +1 when I deformed that smash product earlier on. And then the final relation is that this morphism, this right arrow cup column vector, which is actually a morphism in the additive envelope of this category. So it's going from up, down, directs on the identity to down, up. I need that this has a two-sided inverse. So I'm imposing that this morphism is an isomorphism by asserting that there's another morphism that's this two-sided inverse out there. And I denote this two-sided inverse, of course, it's going to be a row vector, because this was a column vector, it's going in the other direction. I denote that by the leftward crossing and this leftward cap. And you can also introduce a leftward cup, which is just defined in terms of other morphisms that we've got sitting in front of us. So this is this leftward crossing after this rightward cup with a dot. It's kind of crazy, but you think about it and it's exactly the right thing. So that's kind of a very quick guide to the Heisenberg category. I mean, it's kind of remarkably naive definition, just imposing this one morphism being invertible, motivated by the Mackey isomorphism. It turns out it gives you exactly the right object. And so you can study this thing, and it takes a bit of time, but let me just write down a few favorable properties of this category. It's a strictly pivotal category. So that means you can work with these diagrams up to isotopy in a natural way. The center, Z, so the endomorphisms of the unit object in this monoidal category. This turns out just to be a free polynomial ring generated by these dotted bubbles, all of these dotted bubbles for all n greater or equal to 1. So it's an infinite rank polynomial algebra, just generated by those guys. And then a general morphism space in this monoidal category highs, they're all modules over the center, of course. And it turns out that all the morphism spaces are just free as modules over the center. And there's a sort of an obvious basis given by kind of reduced diagrams where no string crosses another string twice and so on. So there's a sort of obvious basis of reduced diagrams. And then you've got these dots. You can put some number of dots on the end. Why not a row vector is used from two objects to one object? I guess I use the same conventions as I use in linear algebra. An m by n matrix goes from Rn to Rm. So that's all there. Was a question. Okay, so that's Heisenberg category. It's you know, of all of these monoidal categories, I think this is one of the very simplest ones. The relations are really kind of very clean and tidy. Okay, so I've finally got this set up. We've got the Heisenberg algebra, little highs. We've got the Heisenberg category, big highs. And now I'm going to try and prove the theorem that the Grothendieck ring of the Heisenberg category is the Heisenberg algebra. Okay. So here's the theorem. These are isomorphic as rings, and the isomorphism is going to send the endomorphisms S lambda plus or minus, which we had in the Heisenberg algebra. So S lambda plus, remember that was multiplication by the Schur function, and S lambda minus was the adjoint operator, just acting on the ring of symmetric functions. So it's going to send those guys, which generate this ring little highs, to the isomorphism classes of the projectives for the category highs that are big S lambda plus and minus. So big S lambda plus, that's the projective defined by Young's idempotent associated to the partition lambda. So the idempotent that defines that spectre module S lambda. The plus part is up arrows. So you take that idempotent, you think of it in the endomorphisms of the right number of up arrows, depending on the size of the partition lambda. And then capital S lambda minus, that's just the dual object. This category is strictly pivotal. So you just rotate your diagrams to 180 degrees. So that's the other object. So it's automatic that this is dual. So that's what we've got to try and prove now. I think I've got it set up to explain a little bit what's going on. So the key to the proof, I mean, the proof's not kind of a big surprise. We've got this Heisenberg algebra which acts on the ring of symmetric functions, and we've upgraded things to categories. That we replaced symmetric functions by this symmetric category. We've replaced the Heisenberg category, the Heisenberg algebra by this Heisenberg category. We concocted the Heisenberg category exactly so that it acts on the symmetric category, right? The relations, the defining relations for the Heisenberg category came from the relations between those obvious natural transformations of those endofunctors of the symmetric category. So it's kind of automatic that the Heisenberg category acts on the symmetric category. Put it in fancier language, the symmetric category is just a module category over the Heisenberg category. So now I'm going to construct a commuting diagram. So at the top of the diagram is that's just our Heisenberg algebra, which acts on symmetric functions. So there's a homomorphism, an algebra homomorphism I'm just calling act, from little highs to endomorphisms of little sim. And similarly, at the bottom of this is the Grothendieck ring of our Heisenberg category. The Heisenberg category acts on the symmetric category, and so that action induces another algebra homomorphism from that Grothendieck ring to endomorphisms of the Grothendieck group of the symmetric category, right? So this just sends X, some object in the Heisenberg category, or some projective, some idempotent if you think in those terms, to the endomorphism of the Grothendieck ring of the symmetric category, just given by acting with X, acting with the corresponding functor. And so we've got these two arrows in this diagram. Of course, the symmetric functions is the Grothendieck ring of the symmetric category. So this is just the obvious algebra isomorphism gotten by making that identification, identifying little sim with K0 of big sim. Okay, so we've got those three. The right-hand one is an isomorphism, and all of those are algebra homomorphisms. And then I need the left-hand arrow in my diagram that makes this thing commute. Okay, and so you just see what goes on. Where does S lambda minus go? Where does S lambda plus go? And so you see the left-hand arrow to make this diagram commute must send the product, little s lambda plus, little s lambda minus, to the class of that tensor product, big S lambda plus tensor, big S mu minus. Okay, so that's that left-hand map. And that's just forced on you so that diagram commutes. Okay, so this is all just sort of a tautology from the way we made this identification and the way we constructed this action, the way we defined S lambda plus, the functor was by this induction product with the spec module. So that just forces this diagram to commute. Okay, so are these actions faithful? Right, so now we come to the hard step, right? We've got this commuting diagram. We do not know at this point that this left-hand map is even an algebra homomorphism. It's just a Z module homomorphism, sending these basis vectors S lambda plus S mu minus to these classes down at the bottom. We haven't even proved that this is an algebra homomorphism yet. It's just a homomorphism of Abelian groups. So now the hard step is to actually show that this left-hand map is actually an isomorphism of Abelian groups. So that's what we've got to do. That's the sticking point in the whole game, is how to show that that left-hand map is an isomorphism. This top map is injective. This action of Heisenberg algebra on symmetric functions, which is often called the Fock space, that's faithful. So given everything else, that means that that guy is injective. And then because the other three maps are algebra homomorphisms, it then follows that that left-hand map is actually an algebra isomorphism, and that proves the theorem. Okay, so all we've got to do is do this hard step. We've got to prove that this left-hand map, which is a Z module homomorphism, is actually a Z module isomorphism. So I'm going to try and quickly go through that now in the last 5 minutes. So I'm going to turn it into algebra language. So I'm going to let capital A be the path algebra of the Heisenberg category. So I'm just going to forget the monoidal structure, and I'm just thinking of that category as one of these locally unital algebras. So this algebra A, you can decompose it as a direct sum of subalgebras A sub D. Nothing's unital. Everything's merely locally unital here. So this is the locally unital algebras. You can take infinite direct sums. That's what I've got here. So AD is just all of it's just coming from all the idempotents labeled by objects X and Y, where the number of ups minus the number of downs is this integer D. Okay, the generating morphisms for the Heisenberg category, they always preserve the number of ups, take away the number of downs. So this is actually just a direct sum of algebras here. Because the object down tensor up is isomorphic to the object up tensor down, direct sum the unit object. That's essentially our definition of the Heisenberg category, so that's true. We can replace this algebra AD with a Morita equivalent algebra BD, right? We can just throw away a whole load of the idempotents because some of them are redundant due to this isomorphism. And so BD is just where you just take the objects X and Y, where actually all the up arrows appear to the left of the down arrows. Remember, objects X and Y, they're just tensor products of ups and downs. So BD is when all the up arrows are to the left and all the down arrows are to the right. And then BD itself, this locally unital algebra BD, is just a direct union of algebras I'm going to call BD, N. So BD, N is just all of BD where the lengths of those tensor products, so I think of these as just words in these letters up and down. So you take all the words of length less than or equal to n. And obviously BD is just the union of those over all n. So after these reductions, what we're trying to calculate is the Grothendieck group of A. And these reductions tell us is the direct sum over all D of the direct union of the Grothendieck groups of all of these BDNs. So this is just kind of some formal reductions. Now these BDNs are actually now unital algebras. There's only finitely many objects X and Y satisfying these conditions for BDN. So these are actually unital algebras. So in this way, we've kind of just naively reduced to proving that the Grothendieck group of the unital algebra BDN has basis given by the projective modules defined by the idempotents for these tensor products, S lambda plus tensor S mu minus. For partitioned lambda mu, you need lambda minus mu to be D. That was that condition, number of ups minus number of downs is D. And you need the sizes of those partitions are less than or equal to N to be making sense for BDN. So we've reduced it to a question about some unital algebras Grothendieck group, and we're going to prove that by induction on N. So we're now looking at a single BDN, and we're trying to compute its Grothendieck group. So let E in that algebra be the idempotent coming from all the objects X, which are A ups followed by B downs. Of course, we have to have A minus B equal to D because we're talking about BDN. And A and B, so in BDN, I think I wrote that wrong. That's good. I wanted to write A plus B here, sorry. In BDN, A plus B is less than or equal to N. So take all the ones where it's actually less than N. So this is all strictly shorter words. And then the idempotent truncation, EBDNE, is then just BDN minus 1, right? Because we're not allowing those words of length actually N. We're getting strictly shorter words. I mean, I'm just setting up for applying this Quillens Lemma. This basic K0 lemma that I started with. We've got this unital algebra, I've got this idempotent. The idempotent truncation of BDN is the smaller BDN minus 1. And then we've got to look at the quotient by that two-sided ideal. So this is just this quotient. What we're doing is we're just killing morphisms that kind of factor through smaller objects by factoring out that two-sided ideal. That's kind of a standard sort of cellular algebra technique, is the way of thinking of this. So this quotient algebra, so now if you ever have a diagram with a cup or a cap, that becomes 0 in this quotient algebra because it goes through some shorter word. So it follows that this quotient algebra, actually it's just diagrams where you've got all ups and all downs and you've got no cups or caps. So this quotient algebra is just easy to understand. It's just a degenerate affine Hecke algebra on the up strings, a degenerate affine Hecke algebra on the down strings, and then there's this center Z, which you remember was that infinite polynomial algebra with all these bubbles. And I know that's a typo there. That's I should just write. Oh, is it working? I want to just write A plus B equals N there. So now, finally, it's kind of obvious to see that I needed this splitting hypothesis in order to use my basic lemma. Yeah, that's okay. So, so I'm now going to calculate K0 BDN using that split short exact sequence at the beginning. Is going to be K0 of the smaller one, the idempotent truncation, together with, oh dear, K0 of that quotient, which is that guy right there. And this we know by induction, and the K0 of this quotient, this is just this tensor product of degenerate affine Hecke algebras, where we can use that filtered argument from Quillens Lemma to calculate that. So that's just coming from the symmetric group on A letters cross the symmetric group on B letters. This infinite polynomial algebra is kind of irrelevant for K0. And that's it, that's the proof. So I did my best, there we go. I'm gonna just finish with one really quick slide because next week I want to talk about what I think is really cool, which is studying Abelian module categories over these Heisenberg categories. I just did the case when K is -1, but the whole story extends to general central charge. So for a general central charge K, the Heisenberg algebra, it's a Z form for the universal enveloping algebra of the Heisenberg Lie algebra, not specialized at central charge -1, but specialized at central charge K. I wrote down a presentation here for it, but it's not important for us. And then there's this Heisenberg category, capital H Heis K, And that's very similar to what we just defined. It's got two generating objects up and down, and the same four generating morphisms. The only change in the relations is instead of this height 2 column vector that I prescribe to be invertible, you take this height k plus 1 column vector, which is this rightward crossing and then these rightward cups with some number of dots on. You join a two-sided inverse of that. That's if k is greater than or equal to 0. I might have got my rows and columns messed up after all. You never know. It happens sometimes. I think I might have done, never mind. Or you need a row vector for the other k. So the theorem extends to this setting. The Grothendieck ring of this more general Heisenberg category is the Heisenberg algebra. And the proof kind of involves that same commuting diagram, except it's much more difficult to know what to put here, where I just had one copy of symmetric functions. Now you have to take a whole great big tensor product of lots of copies of symmetric functions, and kind of you have to reverse the role of up and down as well. And somehow the sticking point in this generalization is how to construct the Heisenberg category action on this tensor product of symmetric categories. And that's this thing called categorical co-multiplication, which we need to do that. And you need to deform and do things generically in order to be able to make that construction. So that's not going to be relevant at all next week. But next week I'm going to look at module categories over these more general Heisenberg categories, Heis K. I think that's the place to stop.
All right. Thank you, John. Does anyone have any questions?
So which steps were missing in my original paper?
So, I mean, you had all the steps, except that you didn't have this hard step. I mean, so let's find where does that go? That's this diagram here. So you gave so you didn't know how to prove that this left-hand map was an isomorphism of Z modules.
I think I had injectivity, right?
So you had a different way of constructing this map. And you were able to prove that it was injective using the faithfulness of this action.
Yeah.
You had to prove the existence of this map in a different way by checking the relations of by kind of categorifying the defining relations of the Heisenberg algebra, which is kind of nice in another part of the story. But I didn't need to check any, to categorify any relations of the Heisenberg algebra to the Heisenberg category this way, because it just follows from this commuting diagram.
I remember using Quillens theorem, but I mean,
you had Quillens theorem, but you didn't have this basic lemma with this idempotent truncation, this EAE in there. So
you remind me of,
that was.
okay.
That was this fact here, right?
So this is similar to what happens in clarified quantum groups when you take the whole group. So you also one can use this. You can kill by the ideal of U-turns reduced to the small thing.
Yeah, I think this is a very general idea that applies in lots of, I mean, as I said, you see the same idea of kind of killing things that factor through smaller objects. This is sort of the philosophy of the cellular algebras in the finite dimensional setting as well. But I think what's key here is we're in this sort of very non-finite dimensional setting where we have these degenerate affine Hecke algebras appearing. So this Quillens lemma is really the heart of it, and you already had that. You knew that should be something to do with it.
So it's very nice. And then you're saying that it's much harder to do the case when it's not, say, the symmetric group, but a cross product of a symmetric group with some finite.
For example, there's a quantum analog of this Heisenberg category where you replace the degenerate affine Hecke algebra with the actual usual affine Hecke algebra, and I have no idea how to prove how to understand what I mean. The Grothendieck group of the actual affine Hecke algebra should be the same as the Grothendieck group of the finite Hecke algebra.
I mean, this was the work of Tony Licata, and Alistair Savage for the Hecke category, for the Hecke deformation. Saying that if you change from the symmetric group to the Hecke algebra, then you get a different category.
Right.
Alistair and Tony did.
So, right, so there's this kind of quantum Heisenberg. And yeah, this was first defined by Tony and Alistair. I think somehow that probably for k equals -1, and then we wrote another paper with Ben and Alistair where I think we kind of fixed that definition actually, kind of, and generalized it. And our category, even when k is -1, is slightly bigger than they had back in that time.
But does your argument work with the Q-deformed case?
Absolutely not. The place where it doesn't work is this Quillens Lemma.
But so how does it break down?
Because Quillens Lemma needs a filtration so that you can pass to the associated graded. And the degenerate affine Hecke algebra is filtered, and the actual affine Hecke algebra
not the usual affine Hecke, not the usual affine Hecke.
The usual affine Hecke algebra isn't filtered.
So this is still a conjecture.
So yeah, so the sticking point in going to the quantum case, everything's in place except we have absolutely no idea how to calculate the Grothendieck ring of the affine Hecke algebra at generic Q.
It's not even known.
It's not known. I totally expect that it's isomorphic, that the inclusion of the finite Hecke algebra into the affine Hecke algebra induces an isomorphism between Grothendieck groups. But without this filtration, so you can't employ Quillens Lemma, I don't know what to do.
And then you have a different direction where you can add cross products, right? That's a different direction.
Yeah, that's a different story where this is sort of Alistair Savage has developed a lot of this, where you add in a Frobenius algebra into the setup, so that you're kind of constructing Heisenberg algebras that sort of correspond to like Leith products.
Okay, and then so when you switch from k to -k, it's just you flip up and down functors to go from k to -k.
Yeah. So right. So the positive and negative k, there's always this symmetry of just reflecting. And
it's not that you're getting a new category for -k. Just it's the same.
Right. You're not getting in. No. Right. So the subtlety there is how to go from k equals -1 to -5. And of course, k equals 0 is different. Central charge 0 actually, I think, is maybe the most interesting of all, has a somewhat different flavor.
But I mean, do you want to use some DG Frobenius algebras with 0 or like
No, zero is much even. I mean, it's even more naive. But you see, for 0, in the 0 case, you just want up down to be isomorphic to down up.
Okay.
So it's it's kind of very easy, but honestly, it's for most of the Abelian module categories that I'll be talking about next week. Actually, central charge 0 is what acts on most of the examples.
But but this looks like relatively simple, right? If up and down is down.
It is relatively simple, indeed. Yeah, but.
But you also want to have curls. You want to have bijoins.
Yes, yeah, you always want this strictly pivotal property. So yeah, but somehow there's quite a few things in central charge 0 which this is like, I don't know, it's like if you're in negative central charge, you have lowest weight modules, and if you're in positive central charge, you have highest weight modules. But if you're in central charge 0, you need these level 0 modules. They're not highest weight anymore. You need to look at the tensor product of a lowest weight and a highest weight module. So somehow
for central charge 0.
Yeah, it's quite an interesting case, even though the category looks kind of more naive.
Yeah. But do they have a name, or have people studied them?
I think I first wrote this down. I called it, what did I call it? I called it the affine-oriented Brouwer category when I first came across it. Before I realized it had anything to do with this Heisenberg category. I kind of independently kind of got it.
It's in your papers. It's in your papers.
Yeah, yeah. But somehow when I first wrote it down, I was thinking about something totally different. And didn't realize that it was a special case of this same Heisenberg family.
Great talk, thank you.
Any more questions for John? All right, then in that case, John, I have a question. So at the end, when you talked about these Heisenberg categories with central charge not equal to -1, you mentioned this commuting diagram, and somehow the difficulty didn't lie in proving that the square commuted in the same place that it did for c equals -1, right?
Mm-hmm.
Why? I guess that's in the left-hand side where you're trying to prove the isomorphism between k0 of highs and highs. Like, why does that work? Why is that easy for k not equal, or for c not equal to -1?
So what's difficult? When k was -1, what we had was this action of highs on sim.
Mm-hmm.
Which sort of was almost a tautology from the way we discovered the relations for highs. Mm-hmm. So you need to replace sim by this more general Deligne tensor product of a load of copies of sim, mm-hmm. and the kind of dual sim where you reverse the role of induction and restriction. And the problem is to come up with an action of highs k on this thing, so. You've got some module categories over highs, and you want to construct a new action of highs on the Deligne tensor product of those module categories. So you sort of see, if you were doing this at the decategorified level, you'd want a co-multiplication. Mm-hmm, mm-hmm. And so this is sort of some categorical version of that co-multiplication to construct this action. And we find such a thing, but only generically. Somehow the categories are not so interesting when it's generic, mm-hmm. But it's good enough for lots of purposes. There's still, these categories are still semi-simple, so they're not kind of interesting from a module theoretic point of view. Mm-hmm. But you're doing the generic case, so a whole load of important properties you can see very nicely from this sort of generic way of getting categorical co-multiplication.
Okay.
So I think that was a kind of a big idea. And that same idea, it appears in all of these categorified quantum group settings where Ben Webster has a way of defining a co-multiplication, but only generically.
I see. Okay, I guess I don't see, so once you have this action defined, how does that give you that the left-hand side of this commuting diagram is just easy, the isomorphism? Why is that? Hard, I guess.
In general K, the proof that this is an isomorphism is actually the same proof as in K is -1.
Okay, that was my question.
That part of the story is the same,
mm-hmm, mm-hmm.
But somehow it becomes difficult in general K to construct this action.
I see.
In the first place.
Okay, thank you.
I have a naive question. So you can think of Heisenberg as some kind of double of symmetric functions where you have symmetric functions with a product and coproduct and mm-hmm. structure. So mm-hmm. is there any way to see this coproduct, for example, on symmetric functions or on the Heisenberg in clarification?
So I mean that this is this categorical coproduct co-multiplication that I haven't talked about, and somehow we have a way of. I mean, that's a whole nother story, but there is there's a monoidal functor. Maybe I can say just a little bit. If you're just looking at sim, you can take this symmetric product of two copies of sim. So what we do when we're doing it, we call this the red copy and the other one the blue copy. And you just take the union of the generators and relations, and then you add some more crossings which let red and blue commute with each other. So there's that symmetric product. and we can actually define that there's a monoidal functor there, which is, it just sends, I guess you need to pass to the additive envelope. Just sending the generating object to a direct sum, and it's kind of totally automatic in that case, because this is the free symmetric monoidal category on one object. You just using that universal property, you see that there's a monoidal functor, and when you pass to the Grothendieck ring, that functor becomes exactly the co-multiplication on symmetric functions. So it's a very naive way of categorifying that co-multiplication. But when you go up to the Heisenberg, like maybe L plus M, you try to do the same thing, and it's not possible to do it. You have to invert some morphism. You have to pass to some localization before you can do it. And so that's this generic thing that happens, and why we only have this generic co-multiplication. But providing you've inverted some morphism, it's possible, and there is this categorical co-multiplication there, which lets you take tensor products of module categories, providing there's some genericity holding. And it's a simple idea, but it's extremely useful. A whole load of things that for example, I didn't talk about how you prove the basis theorem for morphism spaces in this Heisenberg category. It's easy to come up with some spanning bunch of morphisms, but to prove linear independence, you need some large module category that it acts on, and you only need that generically. And this is the perfect tool for constructing kind of generic large module categories that Heisenberg acts on, and proving things like basis theorems. This same categorical co-multiplication works in categorified quantum groups, and I suspect other examples too, and it's a very useful tool for dealing with some of these problems.
John, when you write L, do you mean Heisenberg at level L? So that would be some cross product with an algebra of dimension L?
No, so I have this Heis K, which is central charge K.
Yeah, and they act on.
And so the Heis L is central charge L, Heis M is central charge M. Of course, if you're looking at the Heisenberg Lie algebra, taking tensor product of modules, you add central charges, and so that's all.
So this Heis is not categorified. This is the algebra.
No, this is the category with the capital H.
But in the category, you need to make it act on something. You take cross product of a symmetric group with a finite dimensional algebra of dimension K.
So
make it act on something.
Okay, so Heis K acts on something. So Heis K acts, for example, on these level K cyclotomic quotients of the degenerate affine Hecker algebra.
So you have to fix some kind of some version of cross product, or so you want something more sophisticated.
I mean, so I don't quite know what you're.
You don't want to just cross products.
I mean, this level K version of Heis, it acts on level K cyclotomic quotients.
It's not just cross products. It's something more special.
Right. It's something more. I mean, it's coming from this degenerate affine Hecker algebra again, right? You have to take some finite dimensional quotients of degenerate affine Hecker algebra. So it's a filtered deformation of cross product, but.
And you have parameters because you can model out by any polynomial, and you use that.
And that becomes important in getting this, in making these generic things. It's taking polynomials with generic roots.
You'll explain this next time.
Maybe, but I was actually going to try to talk about the general theory of abelian module categories over Heis K. I wasn't going to talk about this categorical co-multiplication. That's just somehow a tool that's.
And so what's the reference for categorical co-multiplication?
So in our paper proving this K0 conjecture of yours, we had that co-multiplication in there.
And also, what's the reference for the k equal to 0 case? For instance, where to look at the diagrammatics?
So let me see. I think, honestly, I think the best place to look is in the paper I'm going to talk about next week, which is this paper with Ben and Alistair again called Heisenberg and Kac-Moody categorification. That's not the right reference, but it's the place where we finally understood everything the best. So I think we explained it the best and included the appropriate references there. So honestly, I think that's the place to start, is that Heisenberg Kac-Moody categorification paper. You know how it is, you always understand things best about 5 years later.
Thank you.
Excellent. Does anyone have any further questions for John?
I think maybe a potentially easy question. I'm not sure. So John, there's this technical condition you need to have the K0, the split exact sequence on the level of K0. Mm-hmm. You need some, this module A mod AEA to be projective, I think.
Are you talking about the one in the assumptions in Quillens Lemma?
I think it was before Quillens. It was before Quillens Lemma.
The basic lemma, maybe?
The basic lemma.
Let's go back to that. So I had this splitting assumption, right? That's what you're talking about?
Yes. So you...
no, that was the wrong lemma right here. Getting there.
Mm-hmm.
Writing.
Yes, so pending... Yeah, so you need A mod AEA to be projective, basically, right? Or sorry, you need this algebra splitting, you said.
I need to be able to split this quotient homomorphism. Yeah.
No, in the application, so do I remember, like, the application of this was when you kill the diagrams with cups and caps in them?
Yeah, exactly.
Is it hard to verify that this splitting?
Absolutely not. No, I mean inside, you know, we've got like up 2 strings and 3 strings or something like that. The degenerate affine Hecke algebra on 2 up strings, tensor 3 down strings sits inside the Heisenberg category. Mm-hmm. Right. So if you only look at morphisms that are upward crossings on the left and downward crossings on the right, that's a subalgebra.
Mm-hmm.
Okay.
You don't create cups or caps by commuting them. So that's the splitting. It's kind of trivial to see.
Excellent. Okay, and is this condition the same thing as saying that if you think about A mod AEA as a bimodule, then it's a projective bimodule? Or sorry, it's a projective on the left and right or something?
I'm not sure right now.
Okay. Okay.
I mean, there's probably some relation, but I would need to.
Because it seemed like something important was that this bimodule, when you tensor it with itself, is idempotent in the sort of naive sense, but it may not be idempotent in the derived sense unless it's also projective on the right and left. So it looks like your condition is the same thing as having.
I'm really using this splitting. I've got these 2 bimodules.
Yeah, but if you look at the functor of tensoring with that bimodule, you think of that thing as an AA bimodule. That functor is idempotent, which I think is relevant to the basic lemma. Mm-hmm. Which you want it to be idempotent in the derived category as well as the naive Abelian category.
I mean, when I'm splitting this short exact sequence, one way is tensoring with this bimodule, and the other way I need to make A into a module over the quotient, right? So. Mm-hmm. So this basic lemma, I still quite sure that the right person can tell me how to deduce it from the 1960s algebraic theory literature. I mean, we just gave a totally complete self-contained proof of it because we needed it, and we couldn't really find the right place to track it down.
Sure. Yeah. Anyway, cool. Thank you.
May I ask a question?
Mm-hmm.
Regarding your next talk, you said you will be talking about Abelian module category. Could you be a little bit more specific? Is it about the fact that your sim category is monoidal and you want to build a representation theory?
So, for example, today's talk was sort of really based around the idea that the symmetric category is a module category over the Heisenberg category. So this for me is Heis minus one. There's the central charge zero Heisenberg category that acts on, for example, representations of the algebraic group GLN, where up arrow acts as tensoring with the natural representation and down arrow acts as tensoring with the dual natural representation. And of course, those functors commute. In fact, Heis zero acts on all sorts of things like category O for GLN and so there's this general theory of studying a general Abelian module category over Heis K. So any Abelian module category. So an Abelian category on which it acts. And it includes just tons and tons of classical examples like representations of symmetric groups and general linear groups or general linear Lie algebras or general linear supergroup, a whole load of all your favorite kind of type A Abelian categories that you've classically studied. This Heisenberg category just acts on those. And there's this totally uniform general machinery for understanding Heisenberg module categories and things like, so these bubbles become very important because they act, they're in the center of the Heisenberg category. So they act as endomorphisms of the identity functor of this Abelian category. So they become central elements on those module categories. And you have to understand central character decompositions and so on. So there's this whole kind of amazing calculus that comes from these Heisenberg actions and a beautiful general machine.
So you're moving towards two categories of representations of Heis K.
Yeah, I'm interested in, exactly. Yeah, that's a good way of saying it. And it includes so many classical examples, and it kind of gives this sort of unifying framework of studying all of these examples in the same way. And I think it's rather satisfactory.
So when you mention the action of Heis zero on representations of a GLN, is it specifically within the algebraic group, or is just usual GLN over complex numbers?
Any category you like involving any form of GLN. Yeah.
But then it's just the usual, some version of the Brouwer category that you'll see here. People call it the Wall-Brouwer category.
Yeah, what I call the oriented Brouwer category. Yeah. So I mean that Heis zero is just the oriented Wall-Brouwer category with these dots added as well. So it's the affinization.
You don't specify the value of a loop. So you don't specify the value of a loop in Heis zero.
You don't specify
n. So n is not fixed.
I mean, n is sort of nothing to do with Heis zero, right? That becomes what one of these. There's one of these bubbles that's central in Heis zero. That sees the parameter n.
Mm-hmm. Okay.
Right. I mean, these bubbles. We'll see this next week. These bubbles in Heis zero will act as central elements, and the kind of the bottom bubble. That of course acts as n. That's sort of the most trivial central element, the identity matrix in GLN.
So you get a family of Abelian categories on which Heis zero acts by specifying the values of the bubbles.
Yeah, I guess that's the way. I mean, there's nothing special about Heis zero. You want to do all Heis Ks, and there's this very natural family of module categories that they act on, which is somehow universal, called generalized cyclotomic quotients.
That's also in your paper.
Yeah. So
So
this is sort of part of this big structure theory of abelian categories over these Heisenberg categories. And of course, it's similar to categorify quantum group structure theory, but there's a big overlap in the two stories.
So you'll explain this next time.
I'll explain some of it next time. Yes.
All right. It seems like we don't have any further questions at the moment. In that case, let's thank John one last time. Thank you again, John, for a fantastic talk.
Yeah. All right.
The slides will be online, and the video will be uploaded to YouTube.
Yeah, what I'll do is I'll fix all my typos in my slides and then send it to Nicole.
That's a great solution. Awesome. And then we'll hopefully see everyone here next week then. Thanks again, John.
Yep.
Bye, everyone.